The universe is expanding outwards. The rate it's growing is called the Hubble constant, and it's the key to working out the age of the universe.
So the Hubble constant might just seem like some, academic number that doesn't mean anything, but that number contains information about the composition, the evolution, and the fate of the universe.
It's an important number, but there's a problem. Our best measurement methods don't match.
It's incredibly frustrating to not know how old the universe is. It's even more frustrating to know that there's two experiments, which are excellent experiments that we firmly believe in, that completely disagree with each other.
My hair fell out a long time ago over this kind of stuff. This has been the #1 question for over half a decade.
There must be something wrong with one of the methods.
There's a definite sense in the community that whichever camp you happen to fall into, the problems lie on the other side of the fence. So if you're mainly working with the cosmic microwave background, you probably think something is up with the distance ladder.
If there's a problem with the distance ladder, there's a prime suspect. The ladder relies on stars that have a predictable brightness called standard candles.
But there's evidence that these stars are not always the same brightness. So if you expect an object to have a particular brightness and it has a different brightness, then whatever conclusion you draw that relies on the brightness of that object is going to be off somewhat.
Think of the stars like streetlights. If one light is broken and dimmer than the others, you might think it's farther away.
The concern with a distance ladder is that if any of the single rungs is not perfect, then the entire ladder might be out of whack by the time you get to the top.
What we need is a fresh approach to measuring the age of the universe.
We're hoping we could bring in a tiebreaker, a referee, a brand new method that didn't care about any of this or any of that, and tell us what is the Hubble constant.
We may have just found one. This observatory doesn't have a telescope. It's hunting for an invisible wave, a disturbance in space-time itself, caused by massive objects accelerating or colliding. It's known as LIGO.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory, and it is a ground-based gravitational wave detector.
A perfectly stabilized beam of laser light bounces in a 5-mile-long L-shaped tunnel. As a gravitational wave passes through the detector, space stretches, forcing the light to travel a tiny bit farther.
You're bouncing a laser over an incredible distance and trying to measure as space-time itself gets stretched and deformed, whether that laser had to travel a tiny bit further or a tiny bit shorter. And a tiny bit here is the width of a single atom over miles and miles of distance.
LIGO has already detected colliding black holes, but it's also received a signal from something less massive.
Neutron stars are the densest thing in the universe other than black holes. They're the last stopping point before you would collapse all the way to form a black hole.
They're the size of Washington, D.C., but they can have the mass of 2 suns. A collision between neutron stars is incredibly powerful.
It's one of the most energetic events in the universe, and it distorts the fabric of space-time very strongly because their gravity is so strong.
But unlike black hole mergers, neutron-star collisions can also send out light. In 2017, LIGO sent out an alert. More than 70 telescopes on Earth and in space swung into action.
This binary neutron-star merger was the first time we'd witnessed gravitational waves and light waves coming from the same event. It was groundbreaking.
This event is ideal for Hubble constant hunters. The light tells us how fast the colliding stars are moving away from us. Gravitational waves give us the distance.
If we know how far away it is and how fast it's moving, that's the Hubble constant.
Having neutron star mergers added to your arsenal of ways of measuring the universe's expansion is great because it's completely independent. It uses physics that's not related to either of the two competing methods we have so far.
Sounds perfect. The result?
So this brand new measurement that we were hoping would be a tiebreaker ended up coming right in between these two extremes. Thanks for the help.
But it might not be as bad as it sounds. The number of neutron star collisions where we've detected gravitational waves and light? 1.
We shouldn't be at all disheartened by the fact that this hasn't actually decided the problem, because there's a huge margin for error when you have just one object.
We would like something like 100 events like this neutron star merger. That might seem like a huge improvement we need, but actually it's very feasible that in the next decade we'll get there.
Gravitational waves may give us a precise age of the universe, but there is a chance they'll tell us the problem isn't with our measurements, but with our understanding of the cosmos.
If we keep getting different answers for the Hubble constant, especially depending on the method we use, that's a big clue that we don't understand something fundamental about the universe's evolution, its makeup, something important.
Our search for the age of the universe just might destroy our model of how we think the cosmos works, plunging physics into chaos. We don't know the age of the universe. We had hoped that the results from our experiments would be like building a bridge, starting at opposite ends and meeting in the middle.
As time goes on, as the evidence accumulates, these two sides of the bridge are not gonna meet. Something has to give.
Some believe the problem lies in the way we've interpreted the picture of the early universe, the pattern hidden in the cosmic microwave background.
We're really confident in the data that we have from the CMB, but it's actually an indirect measurement of the universe's age. It depends on our model of the universe being right.
It could very well be that our fundamental cosmological model that we've used to successfully describe the universe is coming up short, that there's something wrong in there, that engine is broken.
That engine is the standard cosmological model. Based on our knowledge of particle physics and general relativity, it's like an instruction manual for how the universe works. Rewriting it is a radical suggestion. For the most part, it matches what we see. But it does struggle with one thing.
As the universe expands away from the Big Bang, the intuitive thing you would expect is for gravity to start pulling it back together again. So over time, gravity would just reverse that and pull everything back in, back to a single point.
But what we see in the data is completely opposite. What we see is that the universe is not only continuing to expand, but it's speeding up faster and faster all the time.
To explain this weird phenomenon, the cosmological model relies on the existence of a strange, unknown force, dark energy.
Dark energy is the most perplexing and mysterious thing I've encountered in my research.
Dark energy is a term that we slap on this idea that the universal expansion is accelerating. That's about all we know about it. We don't know what's causing it, we don't know how it behaves, we don't know what it was like in the past or what it's like in the future. So we just call it dark energy.
It's invisible. It fills the whole universe and pushes galaxies apart.
In some sense, it's like a spring, a contracted spring, and you let it go and it wants to push everything away.
And things get stranger. Dark energy doesn't dilute as the universe expands.
As empty space gets created or expands, the dark energy associated with that stays the same. It basically populates all this empty space.
Imagine I'm draining a bucket of water and water just magically appears out of nowhere. That's like how dark energy behaves as the universe is expanding.
Because dark energy increases as the universe spreads out, it makes up more and more of the total energy in our cosmos as time goes on.
At the early phases of the universe, the first 5 billion years or so, the positively gravitating stuff like matter, dark matter, and light dominated the dark energy.